Hey guys, welcome to Electrochem lecture number 2, where we get to look at how we are going to use redox reactions to get a flow of electrons across a wire or to create some usable electricity or electrochemical work. So this diagram that you see down below is a diagram of what we call a voltaic cell. It's also known as a galvanic cell. Those are synonymous. And the other term we often just use is electrochemical cell. And what an electrochemical cell does is it is a device that allows for the transfer of electrons through an external pathway between species in a redox reaction. Now, by an external pathway, I'm referring to a wire. And when we get this flow of electrons across a wire, what we've got is electricity, or the ability to do electrical work, which is awesome. And if you guys choose to do the little at-home electrochemistry demo, you're going to actually be able to create an electrochemical cell that can do work like lighting up a light bulb, turning a fan, anything that you would typically use a battery or electrical power from an outlet in your wall to do. Of course, we're going to have a very low voltage electrochemical cell, so we're not going to be able to do a lot of work, but we'll be able to do some. And the way that we get this transfer of electrons to happen spontaneously, so that's the other key thing here about voltaic and galvanic cells, is these are spontaneous reactions. There are other types of cells that are not spontaneous that we actually have to make occur. But voltaic cells and galvanic cells are characteristically spontaneous. And so the question is like, how do we get electrons to transfer spontaneously from one species to another? We have to take advantage of something called reduction potentials. So before we even look at our cell in detail, let's talk about the fact that electrochemical cells, so our notes from over here, these things take advantage of the difference in reduction potentials these are denoted as E naught, standard reduction potentials of different species. Oops, that doesn't look like an F. Now, these different species are typically metals. You know, in this electrochemical cell, we're talking about the reduction potential of different metals, but it doesn't have to be metals. In fact, all elements have reduction potentials. But in the batteries that we're going to make, we're going to be making those batteries using two different metals. Now, we haven't talked about reduction potentials in a long time, maybe not since chapter 4, if we talked about it then at all. My memory escapes me. So reduction potentials, you can think about a reduction potential, which is E naught reduction, as the amount of voltage produced when a substance gains electrons. Because remember, reduction is the gain of electrons. Now remember, they have to be getting those electrons from somewhere. Like those electrons have to be going to that species from somewhere else. And so these standard reduction potentials, this measure of the love for electrons, you could think about it, you know, I know we've called electronegativity love for electrons, but when we're talking about an electrochemical cell, you actually can think about E naught reduction as love for electrons. It's how much voltage gets created when electrons flow towards that substance. So it is in fact sort of a measure of love for electrons. But like I was saying, those electrons have to come from somewhere. So these are relative values. And the reduction potentials list that I'm going to have you guys use is measured against hydrogen. So these reduction potentials that you're going to find listed in your textbook, as well as both within the chapter 20 text, as well as at the end of your textbook in Appendix E. These reduction potentials are all measured against hydrogen. So for this case, not all reduction potentials are measured against hydrogen, but in this case they are. So gains electrons as compared to hydrogen. So the standard electrode being hydrogen, and we're going to compare how much all of the substances want the electrons compared to how much hydrogen wants electrons. So there's two different lists that you guys can look at reduction potentials. One of them is on page 841. So now would be a good time to pause and go open up your textbook. Page 841, table 20.1. If you look at that table, what you see are a bunch of reduction reactions. And the E naught reduction, given in volts, for a bunch of different species. So up at the top of that list, you can see that fluorine, F2, when it gains 2 electrons, becomes 2F1, that produces a big positive voltage. So if I were to, if you're not looking at your table, shame on you, but fine, I'll write it out for you. F2, when it gains 2 electrons, become 2F minus. It has an E naught reduction equal to positive 2.87. Now these positive voltages, these are favorable, right? We want to create some positive voltage in our systems. If we compare, and that makes sense, right? You guys, like we think about fluorine, like fluorine really wants electrons. So it would make sense that fluorine would have a nice, big, positive reduction potential because it wants those 2 electrons. Let's keep looking down our list here at things that we want less than that. So for example, let's look, and we're going to use this. Let's look at what happens when copper ions in solution, when they gain electrons to become copper solid. That E naught reduction is equal to positive 0.34 volts. Oh, I didn't do a good job up here. That should be volts. This should have matter here. This should be aqueous. This should be gas. Okay. So if I was comparing these two reduction potentials, I would say that fluorine wants 2 electrons more than copper 2 plus wants 2 electrons because the fluorine has a larger reduction potential. Now again, remember these are as compared to hydrogen. So this is as if hydrogen was providing these electrons. So you can see 3.1, the 0 is for the reduction of hydrogen. Okay, so we're comparing everybody to hydrogen here. Go ahead and that. So if 2H plus ions were to gain 2 electrons, become hydrogen gas, this is what we are comparing everybody against. So these values, these standard values were measured in series. Copper was put in series with hydrogen and measured how much the electrons flowed towards the copper ions. If we go down below to, let's say, zinc 2 plus, zinc 2 plus doesn't really want those 2 electrons to become zinc solid. The E naught reduction potential for zinc ions to gain electrons is a negative value, negative 0.76 volts. That's not favorable. That means, like, as compared to hydrogen, that's not what's going to happen. zinc 2 plus is not going to steal those 2 electrons. It would take an application of voltage to get that to happen. It would not happen spontaneously. So these negative reduction potentials are not favorable. The positive reduction potentials are favorable. And if we keep going down this list, you guys might start to notice that this is like an upside down activity series. Lithium 1 plus. Do lithium 1 plus ions want electrons to become lithium solid? Heck no, right? Like lithium wants to lose electrons, right? Remember the alkali metals, 1 valence electron, they really want to get rid of that electron. So it's much more likely that the reverse or the oxidation of this reaction would be what was taking place. This reduction is not likely. In fact, it's got a very large negative reduction potential, negative 3.05 volts. The reverse reaction of lithium losing that electron, the oxidation potential of that would be a positive 3.05 volts. So it's much more likely that this is going to be oxidized. So do you guys kind of notice how it's like an upside down activity series here, right? So this is actually where our activity series comes from. Before you just took my word about like who's hot and who's not. But really an activity series comes from a measure of who wants electrons and who doesn't want electrons. So if I were to reverse this reaction, we would have the oxidation half reaction, and I would get a positive potential. Okay, so this is what I mean by reduction potentials. And so what an electrochemical cell will do is it will take advantage of the fact that copper, this reaction here, that copper ions really want electrons as compared to zinc ions, which don't really want electrons. We can take advantage of this difference in reduction potential between zinc metal and copper metal to create a spontaneous flow of electrons from zinc to the copper. So let's take a look at our electrochemical cell and we'll come back to these reduction potentials here in a second. Okay. So pause the video and go ahead and diagram for yourself this electrochemical cell or this particular setup. And this setup can be between any different number of species. This happens to be a zinc and copper electrochemical cell, but it doesn't have to be. So go ahead and pause and draw that. And welcome back. I'm going to go ahead and start labeling some things in this electrochemical cell. Here on the left-hand side, we have a zinc electrode. So this is like solid zinc. Oops, solid zinc. And it is sitting in a solution of zinc ions. You can see 1 molar being standard values. Oh, I kind of forgot to talk about that, didn't I? We were over here, you know, this E naught. Remember how I've been putting these naught symbols up here? What does this naught symbol mean? This naught means 1 molar concentrations. If we were talking about pressures, it would be 1 atmosphere of pressure, and of course, room temperature, 25 degrees Celsius, 298 Kelvin. So that's what I mean by standard. So in order to use those reduction potentials, I need to make sure that my electrochemical cell has 1 molar concentration here. Now this zinc solution probably came from like zinc nitrate or some other sort of soluble zinc compound, say it's zinc nitrate. So in other words, I've got floating around in this beaker a bunch of zinc 2 plus ions. Over here on the right-hand side of my setup, I have some copper solid electrode, and sitting in a solution probably of, let's say, I don't know, copper nitrate. That's where we got all of these copper 2 plus ions floating around in this solution. So copper 2 plus, a whole bunch of it. And again, that's 1 molar concentration as well. Okay. This salt bridge here, I'll explain a little bit later on. And up here, I have a voltmeter, so I can actually measure the voltage that gets created when I put these two things in series with one another or connected by a wire. So when I look at this setup, I need to ask myself, which one of these metals is going to lose electrons and which one of these cells is going to gain electrons. And so to figure that out, we need to look at the reduction potentials that we were talking about on page 841. You can also find this in appendix. You can find a larger version of the reduction potentials list in appendix E of your textbook. Okay, so if I'm looking at these two reduction potentials, I can see that the copper ions want the electrons more than the zinc ions do, because that would give me a positive reduction potential. So this reduction reaction is the reduction reaction that is going to happen. If copper is going to be reduced, that must mean that the zinc in our particular cell is going to be oxidized. So I'm going to have to flip this reaction because the zinc ions aren't going to get the electrons. The copper ions are going to get the electrons. Where are they going to get those electrons from? From the zinc. So let's go ahead and rewrite those half reactions down here. We said that the copper 2+ ions are going to gain 2 electrons to become copper solid. And that half reaction will produce, I already forgot what it was, 0.34 volts. Awesome. Where are they going to get those 2 electrons from? Those 2 electrons are going to come from the oxidation of the zinc solid. So I'm going to flip that other reaction. There's my zinc losing 2 electrons. That I'm going to call the E0 oxidation because it's not the reduction, it's the reverse. And that originally was a negative 0.76. I'm going to change that to a positive 0.76 volts. Because when you reverse your reactions, you're going to reverse your potentials, reverse your sign. So basically all you do is you look at the 2 metals that are put into your electrochemical cells. You look on your left side, you look on your right side, and you look at their reduction potentials. You take the more negative or less positive, you take the reduction potential of smaller magnitude and you reverse it. Well, I guess I shouldn't say smaller magnitude. You take the more negative one and you reverse it, or the smaller positive one and you reverse it if they're both positive. Because that means that it's less likely to occur. You guys get what I'm saying. The one that's lower on the list, that's the one that you're going to flip. That's the one that's going to be oxidized. So I flipped it, and there are my 2 values. So in other words, here's what's going to be happening up above in my cell. The zinc metal is going to lose electrons. Where are those electrons going to go? They're going to go up and across the wire through my voltmeter, continuing on down onto the copper. So my copper is going to end up negatively charged. All of those electrons are going to come down here onto the copper electrode. That copper solid electrode is just the surface on which this electron transfer is going to take place. And we know that these positive copper atoms are going, or ions, are going to attract to that negative charge. That's where the reduction is going to occur. This is where the Cu2+ will gain their 2 electrons to become copper solid aqueous. Those copper ions are going to grab those 2 electrons and become copper solid. This copper solid electrode is going to gain mass as these copper ions plate onto the copper electrode. As the zinc is oxidized and loses the electrons over here to these copper ions that really want those electrons, this zinc becomes zinc 2 plus. In other words, every atom that loses 2 electrons is going to go off into solution as zinc 2 plus ions. So we're going to create more and more zinc 2 plus over here on this side, as on this side we lose Cu2 plus from solution. So this electrode, because essentially these solid atoms are now going into solution, this electrode is going to lose mass. Because zinc solid atoms are becoming zinc 2 plus ions in solution every time they lose 2 electrons. And so as this is happening, the electrons will just spontaneously flow. So you can see we are now taking advantage of the fact that there is a difference in reduction potential between zinc and copper. And so the electrons are going to flow in that direction. Now, in order for this to continue, we have to maintain electrical neutrality of this system. In other words, we can see here on this side of the cell, in the zinc side, it's becoming increasingly positive over here. And this side is going to be becoming increasingly negative as the copper 2 plus leaves solution, and we're left over with a bunch of excess NO3 1 minus. So to keep this electrical neutrality so that the electrons do in fact flow towards the copper 2 plus, that is the purpose of the salt bridge. And so the salt bridge is usually composed of an aqueous solution of soluble salts. So let's say like KNO3. We want to pick a salt that is not going to precipitate out with anything else. So alkali metal nitrates, very good for our salt bridges. And so let's think about that. We're going to have some K plus available and some NO3 minus available. And the question is like, which direction will the ions in this salt bridge flow in order to maintain electrical neutrality? Well, if this side of the cell is becoming increasingly positive as we produce zinc 2 plus, that must mean that the NO3 minus in the salt bridge is going to flow in that direction to cancel out that excessive positive charge that we have being produced. And here, as we lose copper 2 plus, and the NO3 minus remains, this is going to become increasingly negative in charge. So the potassium ions are going to flow over in this direction to replace those copper 2 plus that we're losing. Okay, now a couple more vocabulary terms on this electrochemical cell. The place where the reduction happens is called the cathode. So the copper electrode is called the cathode. And the place where the oxidation happens is called the anode. You can remember that as anox and red cat. So some animal references to help you remember that. Reduction happens at the cathode, oxidation happens at the anode. So anox and red cat. That's just vocab. When we refer to anodes, the anode in an electrochemical cell is labeled as the negative electrode, and the cathode is the positive electrode. Now, the reason for that, why we say that this is the positive place, is because that is the direction in which the electrons are flowing to. So you can sort of remember it as like, well, these negatively charged things are going to flow towards this positive charge. Another way you can remember that the cathode is the positive part of this cell is this is the direction in which the cations in your salt bridge flow. So the cations flow towards the cathode, and your anions here, the NO3 minus, flow towards your anode. Another way to sort of remember it here for your anode being the negative terminal of your battery is that this is the source of your electrons, right? This is the source of your negative charge. So that's how I keep it all straight. But hopefully it makes sense to you guys. Okay. Last thing I want to look at in this particular cell is how much voltage am I going to get? Like how much electricity is this cell going to produce? And all we have to do to figure that out is just look back down here at our two half reactions. If I were to sum up these two half reactions, I would see my electrons cancel out. And overall, essentially what I have are copper ions and zinc solid producing copper solid. That's that gain in mass of my cathode. And zinc 2 plus ions. All I need to do to figure out what my E naught of my cell is just simply add these two things together to a positive 1.10 volts. This value here, you guys, is called the cell potential. This is the cell potential, or this, I should say, standard cell potential. Because if we were not at 1 molar concentrations, we wouldn't be at standard value. It's also called the EMF, which stands for electromotive force. Because remember, what we're talking about is the amount of voltage that we are going to get in order to do electrical work for us. Maybe we need a little reminder about what a volt is. 1 volt is equal to 1 joule per 1 coulomb of charge. So a volt is equal to a joule per coulomb, amount of energy per unit of charge. Now, let's see if there's anything else. You know, I called this section 20.3, you guys, but really I went into all of this together is 20.3 and 20.4. So I didn't really separate them out. I kind of did that one all at once in there, in that last conversation. So, yeah, I think that's all I need to do. Although, wouldn't it be great if you guys could practice doing an entire setup of an electrochemical cell for yourselves and calculating how much voltage and labeling everything. So maybe I should throw a practice problem at you before I send you off to do a problem set. So let's pick a reaction, shall we? I would like you guys to predict the amount of voltage you get from a setup between works spontaneously. Let's say between nickel and aluminum. Let's do that. Like, let's set up, so practice problem. I would like you guys to draw, label, calculate, all of the things that we just did before for an electrochemical cell between, what did I say? Iron, an iron electrode in iron solution, and aluminum, an aluminum electrode. So go ahead and pause this lecture now. I'm going to actually pause my recording so you don't have to watch me draw at all, and come back with a diagrammed electrochemical cell, and we'll see if we both come up with the same thing. Okay, welcome back. Here is my setup for this electrochemical cell between iron and aluminum. Let's talk about what's happening and see if you guys agree with me. Okay, so the first thing I need to do, obviously, is I need an iron electrode sitting in a solution of iron ions. I need an aluminum electrode sitting in a solution of aluminum ions. Again, they could be nitrates or chlorides. I'm going to need a salt bridge, and I picked a soluble salt like sodium chloride, making sure that my chloride wouldn't precipitate out either with aluminum or with iron. It would not, because I know my solubility rules. And again, if you picked a different salt or if you picked different solutions of aluminum and iron, that's fine as long as they are 1 molar, because we're talking about standard reduction potentials here for this cell. And so now what I need to do is I need to figure out which of these ions is going to gain the electrons and which of these metals is going to lose the electrons in this redox reaction. So to do that, I need to compare the reduction potentials of these two different metals. And if I look up here, I can see that iron's reduction potential is negative 0.44 and aluminum's is negative 1.66. So as compared to hydrogen, these are both not favorable reductions. However, we're not comparing them to hydrogen. We're comparing them in series with one another. And so what I can see here is that the iron ions want the electrons more than aluminum. So in fact, the iron ions will be reduced and the aluminum ions will be oxidized. So this is the reaction that I need to flip or reverse. I can say that aluminum solid in this electrochemical cell will become aluminum 3+ ions in solution by losing their 3 electrons. And in doing so, I now have an E0 oxidation of positive 1.66 volts. Okay, so my aluminum is going to lose the electrons and my iron is going to gain the electrons. Let's draw what that looks like over here. If the aluminum is losing electrons, that means that the electrons are going to be flowing this way. So in our last example, they were flowing left to right. Totally doesn't matter. Left to right, right to left. It's really arbitrary. So the electrons are going to be coming down here onto my iron electrode. My iron electrode is going to become negatively charged, which means that these iron ions are going to attract those electrons and stick onto this electrode. This electrode is going to gain mass. This electrode is where the reduction is happening. Where the reduction is happening is the cathode, where the reduction occurs. Reduction. And over here, as every aluminum atom loses electrons, they are going to be going into solution, producing more aluminum 3+ ions. This is where the oxidation is happening. You guys can see I'm getting lazy with my states of matter. Where the oxidation is happening, the electrode is going to lose mass. And this is what we call the anode, where the oxidation is occurring. We need to think about which direction these ions in the salt bridge are going to flow. My cations will flow towards my cathode, and my anions will flow towards my anode. Or I could think about it as I need to replace these iron ions as they plate out onto the iron electrode. So I need to replace that positive charge with positive cations from my salt bridge. And I need to neutralize all of this excessive positive charge that we're creating over here with the anions from my salt bridge. And now what's left for us to do is to figure out how much voltage are we going to get from this cell. So if I go back over here to my reactions, I now know that this reduction is not happening. And all I need to do is combine my reduction half reaction and my oxidation half reaction. However, remember, the number of electrons that are gained have to be equal to the number of electrons that are lost. And right now I've got a 2 and a 3. So I need to multiply through by coefficients to make sure those electrons are equal. Now here's the cool thing. Reduction potential is an intensive property. So it doesn't matter how many moles of electrons I'm transferring, this reduction potential here stays the same. So even though I'm going to multiply this guy through times 3 to get to 6 electrons transferred, I don't change my reduction potential. And even though I'm going to multiply this reaction through by 2 to get to those 6 electrons transferred, I'm not going to change my reduction potential. But it will change how I write my overall balanced reaction. So here we go. We're going to have 3 iron 2 plus ions reacting with 2 moles of aluminum solid. Moles, ions, atoms. I realize I'm messing, flipping back and forth between terminology here. To produce 3 moles of iron solid and, what am I doing? 2 moles of aluminum ions in solution. So there's my overall redox reaction. And if I want to know what the E naught of this cell is, all I have to do is add together my positive 1.66 volts and my negative 0.44 volts. And if I can do math in my head, that will result in a positive cell potential of 1.22 volts, which is good actually, right? I'm going to get a little more voltage from that cell than I would have gotten from my zinc and my copper cell. So that's it for today. Hopefully I haven't scared you away and you'll be back for Electrochem lecture number 3. All right, good luck.